Have you ever pondered the captivating phenomenon of a dying star unleashing a powerful supernova while leaving its core intact? What exactly comprises these leftover stellar cores following such a cataclysmic event? It's truly bewildering that these stellar remnants defy our expectations by neither disintegrating nor exploding during a supernova. And let's not forget the intriguing enigma of neutron stars, which somehow exist despite neutrons being neutral particles. Furthermore, black holes are not literal holes in space, but rather densely compressed remnants of colossal stellar cores occupying minuscule volumes. What happens to the constituents and elements of these extraordinary celestial objects? Join us on an awe-inspiring cosmic journey as we embark on an exploration of the mysteries surrounding stellar cores, neutron stars, and black holes. Let the journey commence. Ever wondered what triggers a supernova and why it leaves behind a stellar core? A supernova is an immensely potent and explosive event that transpires at the culmination of a star's life cycle. When a massive star consumes its nuclear fuel, it undergoes a catastrophic collapse due to the relentless pull of gravity. This collapse generates a colossal shockwave, causing the star's outer layers to burst forth in a magnificent spectacle of light and energy. However, amidst this violent explosion, the core remains intact, impervious to destruction. The core's tremendous gravitational forces prevent its complete obliteration, leaving behind a compact and dense remnant known as a stellar core. But what precisely constitutes the stellar core? The stellar core that persists following a supernova comprises extraordinarily dense and exotic matter. With the exception of black holes, there are two types of stellar cores: white dwarfs and neutron stars. In the case of a white dwarf, the core primarily consists of densely packed carbon and oxygen nuclei. These remnants emit a faint glow as they gradually cool over billions of years, retaining incredible heat. On the other hand, a neutron star is composed of tightly packed neutrons, formed through the merging of protons and electrons under extreme pressure and temperature. This neutron-rich environment engenders the exceptional properties and immense gravitational pull associated with neutron stars. Unraveling the composition of these stellar cores is pivotal in unraveling the enigmatic nature of these cosmic entities. One might wonder why white dwarfs, predominantly composed of densely packed carbon and oxygen nuclei, and neutron stars, composed of tightly packed neutrons resulting from the merging of protons and electrons, don't simply scatter or disintegrate under the overwhelming nuclear and other forces. After all, conventional wisdom suggests that nuclear and other forces should overpower gravitational forces. So, why do these stellar cores retain their structure and avoid disintegration? The answer lies in the Pauli exclusion principle and the delicate equilibrium between gravity and other forces. The Pauli exclusion principle, a fundamental principle of quantum mechanics, asserts that no two fermions, particles with half-integer spin, like electrons and neutrons, can simultaneously occupy the same quantum state. In the case of white dwarfs and neutron stars, the forceful grip of gravity is counteracted by the electron degeneracy pressure in white dwarfs and the neutron degeneracy pressure in neutron stars. These pressures stem from the Pauli exclusion principle, as electrons and neutrons are compelled to occupy higher energy states to avoid sharing the same quantum state. Consequently, a repulsive force arises, balancing the inward pull of gravity and averting further collapse. It is this delicate equilibrium between gravitational forces and degeneracy pressures that sustains the integrity of stellar cores, preventing disintegration or scattering. Another question might arise. What about black holes? They possess similar particles and fermions in their cores, so shouldn't the Pauli exclusion principle apply to them as well? How is it possible for a black hole to exist? The answer lies in the extreme conditions within a black hole. When a massive star succumbs to its own gravity during a supernova, if the core's mass exceeds the critical threshold known as the Chandrasekhar limit, the gravitational force becomes overwhelmingly intense, surpassing all resistance, including degeneracy pressures. Matter collapses into a singularity, a point of infinite density, where our current understanding of physics crumbles. In this singularity, the laws of quantum mechanics and the Pauli exclusion principle cease to hold. Consequently, matter in a black hole's core is conjectured to compress into an unimaginable density, giving rise to what we refer to as the singularity. This explains why black holes can exist, defying the limitations imposed by the Pauli exclusion principle. Now that we possess this knowledge, you might wonder whether gravity should be considered the strongest force in comparison to nuclear and other forces if it can overpower the Pauli exclusion principle. Does this mean that what we have learned thus far about gravity being the weakest force in the universe is entirely inaccurate? Well, not precisely. Gravity is indeed the weakest force when it comes to interactions between particles at the atomic or subatomic level. However, what distinguishes gravity is its ability to act over vast distances and on massive objects. When an immense concentration of matter occurs within a confined region, as in the case of a collapsing star, gravity emerges as the dominant force, surpassing others. The cumulative effect of gravity acting on such an enormous scale culminates in the formation of black holes. While gravity may seem weaker in certain contexts, its sheer magnitude and influence on astronomical scales enable it to shape the fate of stars and give rise to extraordinary phenomena, like black holes. In conclusion, our voyage into the mysterious realm of stellar cores has uncovered captivating insights. We have delved into the remnants left behind following a supernova, explored the composition of white dwarfs and neutron stars, and contemplated the enigmatic nature of black holes. The delicate balance between gravity, nuclear forces, and the Pauli exclusion principle assumes a vital role in shaping the destiny of these cosmic entities. As stellar cores endure tremendous pressures, black holes stand as an extraordinary culmination where gravity reigns supreme. Our understanding of these phenomena continuously evolves as scientists push the boundaries of knowledge, unraveling the secrets of the universe. Thank you for accompanying us on this captivating exploration of stellar cores and their remarkable destinies. If you found this video enthralling, please give it a thumbs up and subscribe to our channel for more intriguing discussions about the mysteries of the cosmos.